In the mathematics of algebraic topology, the fundamental group is a mathematical group associated to any given pointed topological space that provides a way to determine when two paths, starting and ending at a fixed space point, can be continuously deformed into each other. It records information about the basic shape, or holes, of the topological space. The fundamental group is the first and simplest homotopy group. The fundamental group is a topological invariant. Homeomorphic topological spaces have the same fundamental group. Fundamental groups can be studied using the theory of covering spaces. Since a fundamental group coincides with the group of deck transformations of the associated universal covering space, the abelianization of the fundamental group can be identified with the first homology group of the space. When the topological space is homeomorphic to a simplicial complex, its fundamental group can be described explicitly in terms of generators and relations. Henri Poincaré defined the fundamental group in 1895 in his paper, Analysis Situs. The concept emerged in the theory of Riemann surfaces, in the work of Bernhard Riemann, Poincaré, and Felix Klein. It describes the monodromy properties of complex-valued functions, as well as providing a complete topological classification of closed surfaces. Intuition. Start with a space, and some point in it, and all the loops both starting and ending at this point, paths that start at this point, wander around and eventually return to the starting point. Two loops can be combined together in an obvious way. Travel along the first loop, then along the second. Two loops are considered equivalent if one can be deformed into the other without breaking. The set of all such loops with this method of combining and this equivalence between them is the fundamental group for that particular space. Definition. Let X be a topological space, and let x0 be a point of X. We are interested in the following set of continuous functions called loops with base point x0. Now the fundamental group of X with base point x0 is this set modulo homotopy H equipped with the group multiplication defined by thus the loop fg. First follows the loop f with twice the speed, and then follows g with twice the speed. The product of two homotopy classes of loops, f and g, is then defined as fg, and it can be shown that this product does not depend on the choice of representatives. With the above product, the set of all homotopy classes of loops with base point x0 forms the fundamental group of X at the point x0 and is denoted or simply pi. The identity element is the constant map at the base point, and the inverse of a loop f is the loop g defined by g equals f. That is, g follows f backwards. Although the fundamental group in general depends on the choice of base point, it turns out that, up to isomorphism, this choice makes no difference as long as the space X is path-connected. For path-connected spaces, therefore, we can write pi1 instead of pi1 without ambiguity whenever we care about the isomorphism class only. Examples. Trivial fundamental group in Euclidean space Rn, or any convex subset of Rn, there is only one homotopy class of loops, and the fundamental group is therefore the trivial group with one element. A path-connected space with a trivial fundamental group is said to be simply connected. Infinite cyclic fundamental group the circle. Each homotopy class consists of all loops which wind around the circle a given number of times. The product of a loop which winds around m times and another that winds around n times is a loop which winds around m plus n times. So the fundamental group of the circle is isomorphic to the additive group of integers. This fact can be used to give proofs to the Brouwer fixed-point theorem and the Bors-Coulomb theorem in dimension 2. Since the fundamental group is a homotopy invariant, the theory of the winding number for the complex plane -1 point is the same as for the circle. Free groups of higher rank, unlike the homology groups and higher homotopy groups associated to a topological space. The fundamental group need not be abelian. For example, the fundamental group of the figure 8 is the free group on two letters. More generally, the fundamental group of any graph is a free group. If the graph G is connected, then the rank of the free group is equal to the number of edges not in a spanning tree. The fundamental group of the plane punctured at endpoints is also the free group with n generators. The ith generator is the class of the loop that goes around the ith puncture without going around any other punctures. Knot theory. A somewhat more sophisticated example of a space with a non-abelian fundamental group is the complement of a trefoil knot in R3, as known, whose fundamental group is the braid group. Functoriality. If f, x, y is a continuous map, x0 x and y0 y with f equals y0, then every loop in x with base point x0 can be composed with f to yield a loop in y with base point y0. This operation is compatible with the homotopy equivalence relation and with composition of loops. The resulting group homomorphism, called the induced homomorphism, is written as pi or, more commonly, this mapping from continuous maps to group homomorphisms is compatible with composition of maps and identity morphisms. In other words, we have a functor from the category of topological spaces with base point to the category of groups. It turns out that this functor cannot distinguish maps which are homotopic relative to the base point. If f, g, x, y are continuous maps with f equals g equals y0, and f and g are homotopic relative to x0, then f equals g. As a consequence, two homotopy equivalent path-connected spaces have isomorphic fundamental groups. As an important special case, if X is path-connected, then any two base points give isomorphic fundamental groups, with isomorphism given by a choice of path between the given base points. The fundamental group functor takes products to products and coproducts to coproducts. That is, if X and Y are path-connected, then and if they are also locally contractible, then both formulas generalize to arbitrary products. Furthermore, the latter formula is a special case of the Seifert-Van Kampen theorem, which states that the fundamental group functor takes push-outs along inclusions to push-outs. Fibrations. A generalization of a product of spaces is given by a fibration. Here the total space E is a sort of twisted product of the base space B and the fiber F. In general, the fundamental groups are B, E and F are terms in a long exact sequence involving higher homotopy groups. When all the spaces are connected, this has the following consequences for the fundamental groups. Pi1 and Pi1 are isomorphic if F is simply connected. Pi n plus 1 and Pi n are isomorphic if E is contractible. The latter is often applied to the situation E equals path space of B, F equals loop space of B, or B equals classifying space BG of a topological group G. E equals universal G bundle, e.g. relationship to first homology group. The fundamental groups of a topological space X are related to its first singular homology group, because a loop is also a singular one-cycle. Mapping the homotopy class of each loop at a base point x0 to the homology class of the loop gives a homomorphism from the fundamental group pi1 to the homology group H1. If X is path-connected, then this homomorphism is surjective and its kernel is the commutator subgroup of pi1, and H1 is therefore isomorphic to the abelianization of pi1. This is a special case of the Hurewicz theorem of algebraic topology. Universal covering space. If X is a topological space that is path-connected, locally path-connected and locally simply connected, then it has a simply connected universal covering space on which the fundamental group pi acts freely by deck transformations with quotient space X. This space can be constructed analogously to the fundamental group by taking pairs, where X is a point in X and gamma is a homotopy class of paths from x0 to X, and the action of pi is by concatenation of paths. It is uniquely determined as a covering space. Examples: the circle. The universal cover of a circle S1 is the line R. We have S1 equals R, Z. Thus by 1 equals z for any base point x. The torus. By taking the Cartesian product of two instances of the previous example, we see that the universal cover of a torus T equals S1 times S1 is the plane R2. We have T equals R2, Z2. Thus by 1 equals Z2 for any base point x. Similarly, the fundamental group of the n-dimensional torus equals zinc. Real projective spaces for n1. The real n-dimensional real projective space Pn is obtained by factorizing the n-dimensional sphere Sn by the central symmetry. Pn equals Sn, Z2. Since the n-sphere Sn is simply connected for n2, we conclude that it is the universal cover of the real projective space. Thus the fundamental group of Pn is equal to Z2 for any n2. Lie groups. The fundamental group of a connected Lie group is always commutative. The fundamental group of a compact Lie group can be computed inductively or using the machinery of the associated root system. Either of these methods allows one to show that SU is simply connected for all n, whereas the fundamental group of SU is Z when n equals 2 and Z2 for all larger values of n. Let G be a simply connected compact Lie group, for example the special unitary group SU, and let gamma be a finite subgroup of G. Then the homogeneous space X equals G. Gamma has fundamental group gamma, which acts by right multiplication on the universal covering space G. Among the many variants of this construction, one of the most important is given by locally symmetric spaces X equals gamma G, K, where G is a non-compact simply connected Lie group. K is a maximal compact subgroup of G. Gamma is a discrete countable torsion-free subgroup of G. In this case the fundamental group is gamma and the universal covering space G, K is actually contractible. As an example, take G equals SL, K equals SO and gamma any torsion-free congruence subgroup of the modular group SL. From the explicit realization, it also follows that the universal covering space of a path-connected topological group H is again a path-connected topological group G. Moreover, the covering map is a continuous open homomorphism of G onto H with kernel gamma, a closed discrete normal subgroup of G. Since G is a connected group with a continuous action by conjugation on a discrete group gamma, it must act trivially, so that gamma has to be a subgroup of the center of G. In particular, pi1 equals gamma as an abelian group. This can also easily be seen directly without using covering spaces. The group G is called the universal covering group of H. As the universal covering group suggests, there is an analogy between the fundamental group of a topological group and the center of a group. This is elaborated at lattice of covering groups. Edge path group of a simplicial complex. If X is a connected simplicial complex, an edge path in X is defined to be a chain of vertices connected by edges in X. Two edge paths are said to be edge equivalent if one can be obtained from the other by successively switching between an edge and the two opposite edges of a triangle in X. If V is a fixed vertex in X, an edge loop at V is an edge path starting and ending at V. The edge path group E is defined to be the set of edge equivalence classes of edge loops at V, with product and inverse defined by concatenation and reversal of edge loops. The edge path group is naturally isomorphic to pi1, the fundamental group of the geometric realization, X, of X. Since it depends only on the two skeleton X2 of X, the groups pi1 and pi1 are isomorphic. The edge path group can be described explicitly in terms of generators and relations. If T is a maximal spanning tree in the one skeleton of X, then E is canonically isomorphic to the group with generators and relations. A similar result holds if T is replaced by any simply connected, in particular contractible, subcomplex of X. This often gives a practical way of computing fundamental groups and can be used to show that every finitely presented group arises as the fundamental group of a finite simplicial complex. It is also one of the classical methods used for topological surfaces, which are classified by their fundamental groups. The universal covering space of a finite connected simplicial complex X can also be described directly as a simplicial complex using edge paths. Its vertices are pairs where W is a vertex of X and gamma is an edge equivalence class of paths from V to W. The K-simplices containing correspond naturally to the K-simplices containing W. Each new vertex U of the K-simplex gives an edge W and hence, by concatenation, a new path gamma U from V to U. The points and other vertices of the transported simplex in the universal covering space. The edge path group acts naturally by concatenation, preserving the simplicial structure, and the quotient space is just X. It is well known that this method can also be used to compute the fundamental group of an arbitrary topological space. This was doubtless known to Čech and Leray and explicitly appeared as a remark in a paper by Ondřej Weil. Various other authors such as L. Calabi, W.T. Wu and N. Berikashvili have also published proofs. In the simplest case of a compact space X with a finite open covering in which all non-empty finite intersections of open sets in the covering are contractible, the fundamental group can be identified with the edge path group of the simplicial complex corresponding to the nerve of the covering. Realizability. Every group can be realized as the fundamental group of a connected CW complex of dimension 2. As noted above, though, only free groups can occur as fundamental groups of one-dimensional CW complexes. Every finitely presented group can be realized as the fundamental group of a compact, connected, smooth manifold of dimension 4. But there are severe restrictions on which groups occur as fundamental groups of low-dimensional manifolds. For example, no free abelian group of rank 4 or higher can be realized as the fundamental group of a manifold of dimension 3 or less. Related concepts. The fundamental group measures the one-dimensional whole structure of a space. For studying higher dimensional wholes, the homotopy groups are used. The elements of the nth homotopy group of X are homotopy classes of maps from Sn to X. The set of loops at a particular base point can be studied without regarding homotopic loops as equivalent. This larger object is the loop space. For topological groups, a different group multiplication may be assigned to the set of loops in the space, with pointwise multiplication rather than concatenation. The resulting group is the loop group. Fundamental groupoid. It is convenient to consider a path in S-space is given by a map where, then, are called the initial and final points of the path and is also called the length of, if also is a path such that then we can define a path to be on and on. This composition makes these paths into a category. There are at least two ways of taking homotopy classes of such paths relative to the endpoints. Crowell and Fox use a continuous change of the length, while topology and groupoids uses paths with the same initial and final points are equivalent if there are real numbers such that and are homotopic, i.e. endpoints. Here is the path extended by the constant. This construction yields not a group but a groupoid, the fundamental groupoid of the space. More generally, one can consider the fundamental groupoid on a set A of base points, chosen according to the geometry of the situation. For example, in the case of the circle, which can be represented as the union of two connected open sets whose intersection has two components, one can choose one base point in each component. The exposition of this theory was given in the 1968-1988 editions of the book now available as Topology and Groupoids, which also includes related accounts of covering spaces and orbit spaces. Groth and de Groot in 1984 in Esquisse DUN program. People still obstinately persist, when calculating with fundamental groups, in fixing a single base point, instead of cleverly choosing a whole packet of points which is invariant under the symmetries of the situation, which thus get lost on the way.